Swayam Prabha. Digital India. Educated India.
Hello, this is lecture 7 and we will be continuing with the torsion of non-circular shaft using Prandtl stress function. So, in the last lecture we have seen Prandtl stress function which is given in this form. The two non-zero shear stresses are written in terms of Prandtl stress function, and this stress function should satisfy these two criteria in order to satisfy the equilibrium condition and the boundary condition on the lateral surfaces. We have found out the boundary condition on the top and bottom surfaces left us with these two expressions, that x hat should be equal to tau x z and y hat should be equal to tau y z. Now, we know that the top and bottom surfaces of the cross section are also force free, and the only moment or force that is acting on the shaft is a torsional moment mt. So, now we have to prove that the resultant of x hat and y hat on the top and bottom surfaces are 0. For a non-circular for a circular cross section shaft, it was pretty straightforward and obvious because of the symmetry of the cross section. But for a generalized cross section, this is not so obvious that the resultant of x hat and y hat, where x hat is of this form and y hat is of this form, is going to be 0. So, we are going to prove that they are going to be 0. So, let us proceed with the proof. So, resultant of the force in x direction, let us call it as Sx. So, Sx is going to be the area integral, x hat is the force per unit area. So, the area integral of x hat in dx and dy. So, in place of x hat, I can write this as, in terms of Prandtl stress function, as del var phi by del y into dx by dy. Now, I can write this integral as dx so I can always write this integral in this form. Now, using Green's theorem, this expression can be written as the contour integral of phi over dx. By using Green's theorem, we can convert this integral into a contour integral of phi over dx. Now, from our previous criteria, we know that phi is equal to 0 on the boundary or on the contour. Therefore, this is equal to 0. Therefore, we can say that Sx, which is the resultant of the force x hat on the top and bottom surface, is equal to 0. Let us find out the same thing for the y axis. So, the resultant of the force in y direction, that is Sy, can be similarly written as area integral of y hat, which can be written in terms of Prandtl stress function as which using Green's theorem can be written as minus over the contour, and this is equal to 0 because phi is equal to 0 on the boundary contour. Therefore, we can say that both Sx and Sy is equal to 0. So, we can say that Sx is equal to 0 and Sy is equal to 0. So, this boundary condition therefore produces 0 resultant force in x and y direction. So, that boundary criteria is fulfilled. Now, let us see whether this x hat and y hat, this distribution will produce the torsional moment mt. Now, let us see the expression for mt. Now, the torsional moment that is acting on the shaft mt can be written as x y hat into x minus x hat into y into dx dy, where x hat is the momentum and for y hat force and y is the moment arm for the x hat force. Now, if I expand this, this can be written as minus which can be further written as now, if we use integration by parts, we can convert the above integral in this form. This expression can be obtained by using the integration by part technique. Now, this can further be written as using Green's theorem as a contour integral of phi x into dx, into dy minus the contour integral of phi y into dx plus 2 Again this has to be equal to 0 and this integral also needs to be 0 because phi is equal to 0 on boundary. Similarly, this phi is also equals to 0 on boundary. Therefore, we are just left with this expression. Therefore, mt or the torque applied can be written in terms of the stress function as phi dx into dy. Therefore, if I can find out a Prandtl stress function phi, we can obtain the shear stresses tau x and tau y. It can we can also find out the expression for the torsional moment if we know phi. In the next slide, I will be solving an example which will clear this idea in a better way. Let us move into this example. So, we have a shaft as shown here. This is the shaft. Now, the shaft is in pure torsion, that is the only externally applied force or moment is the torsional moment mt applied at the two ends. Now, x, y, z are the coordinate axis. If I take any arbitrary cross section, the arbitrary cross section is an ellipse given by this equation, where a and b are the major and minor axis, a being greater than b. So, the problem states that a shaft with elliptical cross section is experiencing a torsional moment mt. Find out the torsional rigidity of the shaft and also find out the maximum stress developed in the shaft in terms of the applied torsion mt. Now, we will be using Prandtl stress function to solve this problem. So, the problem is to find out the torsional rigidity. How will we find out the torsional rigidity? We will write the torsional moment mt in terms of theta, and that relation will give us the torsional rigidity Gj, and once we find out, we will find out the expression of the shear stress in terms of mt and find out the maximum value of mt. So, let us proceed. So, we need to find out Prandtl stress function Now, the criteria on the Prandtl stress function is that they need to satisfy the expression and phi needs to be 0 on the boundary. Now, how do we do that? So, I just need to find out a phi which is going to satisfy these two criteria. So, let us make this thing that let us assume that my stress function phi, let it be some m into or some k into the equation of the ellipse itself. Equation of the ellipse itself. Let us assume that let the stress function be of this form. Why have I done that? I have done that because this expression directly satisfies this criteria. Because it is the equation of the ellipse, it directly satisfies that phi is equal to 0 on the lateral boundary. I don't have to put any effort. It directly solves this, satisfy this second criteria, that it is equal to 0 on the lateral boundary. So, one criteria is satisfied. Now, let us see whether this is going to satisfy the first criteria. So, if I substitute this into this equation, what do I get? I get k, I get 2 by a square plus 2 by b square, and that needs to be equal to minus 2 g theta, minus 2 g theta. So, therefore, if k is equal to minus g theta into a square by b square plus a square plus b square, then this criteria is also satisfied. Therefore, the stress function, an ideal stress function, is going to be minus g theta So, this is my ideal stress function, which is satisfying both the criteria of the required for it to be a proper stress function. Now, let us try to find out the expression for the torsional moment in terms of the stress function and also the shear stresses in terms of the stress function. So, we know that from our previous calculation that the torsional moment can be written in terms of stress function as 2. So, I know that is it is minus 2g So, we have to evaluate this integral. If we evaluate this integral, we will obtain the expression of mt in terms of g theta and the geometrical parameters of the cross section. So, this is x is going to be 0 to a and y is going to be 0 to b. Now, if we solve this, then you will see that mt from this expression will be g theta pi a cube b cube by a square plus b square. So, therefore, I have evaluated mt in terms of my stress function and therefore, I have got it in terms of g theta. Now, from this we can say that the torsional rigidity which is obtained as mt is equal to g j into theta. So, from this we get that g j for elliptical cross section is g pi a cube b cube by a square plus b square. So, therefore, this is the torsional rigidity of elliptical cross section shaft. So, the first part of the problem is solved. Now, we need to find out the shear stresses and we need to find out the maximum value of the shear stresses. So, we know that tau x z in terms of Prandtl stress function is del phi by del y. So, if I do that, then I know phi, I know the expression for phi, then tau x z can be written as minus del by del y into minus into phi, which is, this is equal to, phi is equal to minus g theta a square b square by a square plus b square into x square by a square. We know this. So, if I evaluate this, this will be, I'm skipping the intermediate step. This is going to be minus 2g theta a square y by a square plus b square. Then similarly, tau yz can be written as minus del theta by del y, which is, will end up being 2g theta b square x by a square plus b square. Now, now here we can write from equation 5, if this is equation 5, from equation 5 we can say that g theta can be written as mt into a square plus b square by pi a cube b cube. Now, if we use this expression and plug in this equation into the expression for tau xz and tau yz, we get this expression as tau xz is going to be, if we just substitute the value, is going to be minus 2 mty by pi a b cube, and tau yz is going to be 2 mt x by pi a cube b, which was initially I had tau xz to be equal to minus 2g theta a square y by a square plus b square, and this to be 2g theta b square x by a square plus b square. Now, replacing g theta in terms of mt, we have obtained this expression. So, in terms of mt was g theta pi a cube b cube by a square plus b square. So, by plugging this into this equation, we have got this and got this. Now, let us look into this expression and see what would be the maximum shear stress. So, let us find out the maximum value of shear stress. Now, what would be tau xz max? Tau xz max is when y is equal to b. So, that is minus 2 mt into b by pi a b cube, which is minus 2 mt by pi a b square. Similarly, tau yz max is going to happen when y is equal to b. Now, tau yz max is going to happen when x is equal to a, and that is pi a cube b, when x is equal to a, and that is equal to 2 mt by pi A square B. Now, since A is greater than B, therefore, the maximum value of shear stress tau max is going to be tau x z max, and that is going to be minus 2 mt by pi into AB square. So, this is going to be the maximum value of the shear stress. We will not bother about the sign. We are mostly, when we are trying to find out the maximum value of the shear stress, we are mostly concerned with the magnitude of the shear stress. So, depending on the sign of mt, this will be minus or plus. Now, in summary, we can say that given a cross section, if you can find out a suitable stress function which satisfies the two criteria, then from the stress function we can find out the expression for the torsional moment in terms of g theta, and therefore find out the torsional rigidity. Similarly, we can find out the expression for the shear stresses in terms of the stress function using the stress function, and we can find out the maximum value of the shear stresses through inspection. So, with this I will end this lecture. In the next lecture we will solve another example problem, and then we will move on to a new topic. Thank you.